Great, thanks a lot for the invitation, and apologies if I'm a bit slow today. I have this feeling that my body has arrived to California, but my brain is somewhere between Brussels and Hudson Bay. So I'll do my best. So I'd like that we take some time today to first admire this beautiful picture that I believe was taken somewhere in Antarctica, in the Southern Ocean. I love it for many reasons. The first one is that it's just beautiful, and that we maybe need a bit of beauty in this world that is getting so crazy. The second one is that it's very quiet, and it gives me the sense that time is elapsing very slowly, and I really appreciate the chance that we have here, and for me for the coming weeks too, to take the time to do things slowly and to enjoy long presentations where we can ask and answer many questions. I think we are really missing that those days. And the last reason, which is much more pragmatic, is that this summarizes all the complexity of what we are trying to understand in polar regions. You see, obviously, a lot of sea ice here, an iceberg. Here on the back, the ice sheet, and here most likely the terminating phase of the ice sheet, which is the ice shelf. And we can even guess some landfast ice close to the coast. So I think this picture summarizes all the possible interactions we could imagine, plus the atmosphere and the ocean. And what we are doing in our group is really focusing on the sea ice, but trying to understand it as an interacting agent with all the other components. And as you will see, and this will be my running thread in this presentation, it's actually very complicated, and there are many more questions for the next decades to explore. So I'd like to start by coming back 10, 12 years in the past, and this is a slide that I pulled from a presentation I had given at the IGS workshop in Hobart, 2013 or 14, I believe. And at that time, sea ice extent in the Arctic had experienced a very steep decline. And so I came to my presentation showing people this time series that is from a simplified model, but that looked pretty much like the observed sea ice extent at that time. Very moderate decline for the first decade, and a very sharp decline between 2000 and 2012. And so I asked this question: when do you think that a simplified model will go ice-free in summer? And I gave 4 possible answers, A, B, C, D, and without big surprise, I got many A's and B's, a majority of A's and B's, just because I think that people mentally like to extrapolate the data they see, and they probably fitted a quadratic trend to the time series, which led them to give an A or a B answer. And in fact, it was also the time that we had these very concerning interviews in some media, including interview by Pete Wadhams, who was claiming that Arctic sea ice would go ice-free in a couple of years from now being 2028, 2010. And obviously this has not happened yet. And my point with that slide was to tell people, okay, be just careful about the interaction between the force trend and internal climate variability, because in my example, in this simplified model, that model goes ice-free, but much later than what you could have expected from a pure quadratic extrapolation. And I feel that we are pretty much in that situation now, that this member of that simplified model was actually right, because the current values of observed sea ice extent in September is around 4 to 5 million square kilometers in 2025. So that's my point to explain that, yeah, these interactions between force and internal variability are extremely complicated, and we have to be a bit careful also to not install a sort of distrust to the public that we are making false claims about what's going to happen in the future. So what's happening in the Arctic is not, of course, isolated. The same story holds for Antarctic. So this is Arctic. The bottom is Antarctic sea ice extent, where, as you know, there has been this this slight expansion over the years. And starting from 2015 or so, we have experienced a massive flip in the sea ice extent anomalies, where we have been breaking many records year to year. And so this gives me somehow hope that we still have a lot of papers to write and proposals to submit. We were convinced the story was all written, that we had an expansion of Antarctic sea ice and a decline in Arctic sea ice and periods, but the recent years have really told us that there are many more things to understand. So the plan for today is to try to browse you through many questions that we are trying to answer in our group, mostly related to sea ice variability at the subdecadal time scale. The first one is what happened to Antarctic sea ice recently. We are going to focus on one case study because I believe this is one good way to understand the physics of sea ice in Antarctica. The second is that we are going to try to imagine what sea ice could be, how extreme could sea ice become in the worst case. So really looking at black swans, if you know the term. So this very low probability, possibly high risk event. Then we are going to ask what could happen in the Arctic for the next years, but also whether CMIP 5, CMIP 6 models are able to predict those variations. A few words on machine learning based predictions, because they are making a lot of noise at the moment and we would like to question whether they are useful or not. And finally, I will touch a word on physical model developments, including all the interactions between sea ice and surrounding agents. So let's start by just introducing the people who work in our group, based in Belgium, in a city called Louvain. You're always welcome to come around if you're in Europe. So we are 22 at the moment, a mix of academics, postdocs, and PhD students. I won't go through them all, but you may recognize a few familiar faces, and Danny is with us today. I will talk a bit about work that Danny has been involved to later in the talk. In terms of tools, we are mostly using an ocean sea ice model called NEMO, coupled to the sea ice cube model. Sea ice cube is now the European sea ice model that has been resulting from the fusion of 3 European models, and we are using it now on a daily basis. And we run that model at typically 3 to 4 spatial resolutions, 1 degree, 1/4 degree, which is eddy permitting, 1/12 of a degree, and then a regional configuration at 1/24 of a degree. Besides that, we also run a coupled climate model called EC Earth. We saw today a few results from EC Earth for housing experiments, and EC Earth is typically run at 1 degree resolution. So let's start with Antarctic sea ice. And as I said, we find it very useful to look at particular cases to understand how things behave. And so we looked at the 2023 summer sea ice extent record that, to my knowledge, is still the lowest Antarctic sea ice extent on record. And what was really interesting about that event is that it was dominated by dynamics that occurred in the Eastern Ross Sea. Actually, so the record is in February 2023, around here, but you see that the sea ice conditions were below average for most of the regions, except in the Eastern Ross Sea where they were positive. So there was a positive sea ice extent edge anomaly in the Eastern Ross Sea that massively flipped to a negative sign and drove the record until February. So that was the starting point of the analysis, is what's happening in the Eastern Ross Sea. And so for that, we used observation and this NEMO ocean sea ice model, and we really proceeded by chronologically, starting 12 months before the record and going month by month to look at the maps and try to understand what was going on. And so we started in the season before the record. We start in autumn, so after the previous record, after the previous minimum in summer, and we noticed that massive Amundsen silo deepening that installed itself and that started to wobble a bit around its usual climatological location, and that Amundsen silo produced winds that, as you know, pushed the ice away in the Ross Sea and eventually created this massive anomaly in the sea ice concentration offshore because of the dynamic effect and the dynamic transport of by the winds of the sea ice. So this anomaly positive that we saw in the eastern Ross Sea was mostly caused by atmospheric patterns. But then in summer, so this is where we try to explain the record. In summer, of course, we noticed that this anomaly had disappeared because it's equator wall and it would have melted anyway. But we noticed a strong negative anomaly in sea ice concentration near the coast. And so our intuition put us to surmise that it could be due to thermodynamic processes, due maybe to divergence caused by the winds. And so we decided to look at the mass balance terms in an ocean sea ice model to understand what was going on there. So for this, we looked first at the climatological mass balance in that model, where you see that there is a contribution during the melt from the sulfates, from the lateral processes, the basal melt, etc., etc. And then we compare to what actually occurred in 2022 to 2023 melting season. And very interestingly, we noticed this very early development of a surface melt process that we found out was related to anomalously thin ice cover, but also to a small snow cover. And then after the surface melt, we noticed a kick from the basal melt here in purple that led us to believe that there must have been an interplay between surface and then basal melt through the ice albedo feedback playing a strong role in that region. So that's, I think it's a nice way to understand how a record can be broken, first focusing on the regions, because understanding just the extent record by itself doesn't make any sense. We have to go to the regions and then trying to blend observational data and modeling data to understand the physics behind that record. The second question is, how extreme can a sea ice record be? For that, the starting point of this analysis is that the time series of Arctic sea ice extent that we are all familiar with is only one sample of the possible climates. And most importantly, these records, like 2007 and 2012, by definition, they are rare events, and so we cannot oversample them. So if we want to study the statistics of those events, we need to have other ways. And so recently, there has been a very fresh input of the field of physical statistics into climate science, where it becomes possible to oversample these rare events by applying a procedure where we kill and clone particles that are not, let's say, we kill those particles that are not extreme enough, and we clone those particles that are super extreme. So the idea is that we have a dynamical model, we integrate it forward in time, and at every time step, or every month, let's say, we just get rid of all the particles that are too normal, and we keep the extreme particles, and then we resample the trajectories from that extreme members, and we keep going like that, so that we always stay in the most extreme part of the spectrum of the distribution of the sea ice state. So this is if you want to keep the highest values, and this is typically what people do for studying heat waves, for example, when they want to understand what would be the worst heat wave we could get. But of course, you can flip the sign and apply that to the sea ice extent. So Jérôme Zauer did that for the sea ice by looking at a melting season from March to September, and he constantly, every month, retained those particles that have the lowest sea ice extent until producing the lowest possible sea ice extent in September. This technique is called the rare event algorithm. It has some relationship with ensemble boosting that some of you may know from other papers, although this method is mathematically a bit more well-defined and robust statistically. So what does it give? Very interesting results. First, if we look at a simple control run, we would have by definition, a probability density function that would be centered around 0 by construction. Then if we start to apply this algorithm, then you see we are able to efficiently sample the extreme left tail of the distribution. And also we are able to construct diagrams where we plot the return time or the probability of occurrence as a function of the sea ice area. And we can actually go much more to the small probabilities or the large return times than we could do with a control run. So statistically, it provides a really robust and really sound quantification of how extreme we could expect sea ice to be, at least in that model. By the way, the model was, in that case, very simple. It's the PLASM sea ice model, so it's a coupled model, but with very low resolution, and we are now transitioning to GCM simulations. So that's the first aspect, is that it can quantify the statistical rareness of the event. The other advantage is that all the particles that you are oversampling, they're always dynamically and physically in balance. So they are consistent with themselves. They are not like particles where you have added increments like you would do in data simulation, for example. So you keep members, or you keep particles that are always physically interpretable. And so what we have done is to try to understand what is the ideal recipe for cooking a worst sea ice extent in the Arctic. So starting from September, where we can define this probability density function by oversampling the rare events, we can move backward in time and look at what are many parameters, fluxes, preconditioning, sea ice thickness, in those particles that led to the extreme tail of the distribution. And so we found first, and that was not a big surprise, because there's been much literature on that sea ice thickness anomalies are a strong preconditioner to generate those sea ice extremes, especially in May-June. So that was half of a surprise because it's been reported before. But then we could also understand why sea ice thickness was so negative in terms of anomaly, and we found a very strong role for downwelling long-wave radiation caused by a strong presence of clouds and also much moisture in the Arctic atmosphere, at least in the model. So it really seems that the state of the atmosphere in late winter is a key to generate those sea ice thickness anomalies that in turn will cause the sea ice extent anomalies. The other important element is that the surface, the ice albedo feedback seems to play a strong role. As you see here, so when the long wave radiation goes back to climatology, then there is the short wave fluxes that take over, and that will kick the sea ice extent decrease even further. And we found a strong role of the net shortwave radiation flux caused by the cloud anomaly. So it really seems that to produce this ideal, I'm not sure ideal is the right word, but this worst case sea ice extent, you need to have this strong interplay between moisture, clouds, that play different role as the season progresses, and also a strong preconditioning of the sea ice state. So this is very interesting, and as I said, we are now moving to a full-blown global climate model, namely EC Earth, where we have interactive dynamics. In the PLASM model, there is no dynamics, so it really also limits the reach of the conclusions. And what we find with ECRs is that the dynamics actually plays a big role. In particular, the strength of the Beaufort gyre is a strong helper to generate those sea ice extent predictions. So let's continue with the fluctuations prediction by climate models. And one of the big projects we've been working on over the past years is on trying to understand rapid sea ice loss events in the Arctic. So RILES, R-I-L-E-Es, RILES. So this is a term that I think was introduced by Marika a few 15 years ago, no, 2006. Abrupt sea ice decline. So these are events where the sea ice extent decreases much faster than the forced trend, and where you could lose a significant share of the mean state in a couple of years. And so these are events that are present in many climate models, many CMIP 5, CMIP 6 like climate models. And obviously these are events that you don't see in ensemble means or in multimodal ensemble means, because you have by definition averaged out all the variability. And so the motivation for studying these RILES is that in observations, we seem to be in a period where sea ice extent has declined very slowly over the past 10 years or so. And so, given that this follows a period where sea ice extent has been declining much faster, we might question whether the next decade or so could also be featured by a RILE. So it could be that sooner or later, the sea ice extent will resume to the forced trend, or even swing to a more negative anomaly and produce a very sharp decline in sea ice extent. So obviously this is a very concerning question, but we want to, in this project, to quantify the ability of current climate models to predict these, let's say, high-frequency fluctuations. And so the starting point of the analysis was to first produce a climatology or an anatomy of these RILES in CMIP models. And so Annelies Sticker, who is doing a PhD student, thesis, has really made a fantastic inventory of all these RILES in CMIP 6 models by season, by year, and by climate model. So whenever you see black, means that one RILE has been detected in that model for that year, for that season. And very interestingly, we see that first RILES occur in all seasons and in all models, as I said. So these are really features that that are to be expected. By the way, if we apply the RILE detection algorithm to the observed sea ice extent, we don't see a RILE yet. Even the first decade was not sufficient to be a RILE. And then the second interesting aspect is that the winter RILE seems to be much more consistent seasonally than the summer RILES, which seem to be a bit more random and scattered through the century. So there seems to be some structure, at least in winter, and yet many mechanisms to be understood. Then the next question is whether the observed trend over the past 10 years or so are compatible with climate internal variability. I don't know about you, but I've been called several times by journalists who are reporting messages on social networks by climate denialists who are claiming that Arctic sea ice decline has stopped. So we should be very careful about using the term pause as we speak, not because it's not a pause, but it can be really overinterpreted. I think that Arctic sea ice decline is continuing. It's just that you need to take the full view, and you need to recognize that climate trends are built on decades, not on 5 or 10 years. But I think it's a very legitimate question to ask whether this blue trend is compatible with the statistical distribution of all possible trends. And so Patricia de Repentigny, who is now in the University of Ottawa, but who worked with us for a couple of years, has produced these histograms of all possible 12-year trends and then 45-year trends from the CMIP6 model, and has placed the 2000 to 2011 trend here in purple, and then the 2011 to 2023 trend in blue, in cyan. And you can actually see that the purple trend is more unlikely than the cyan trend is compared to the background distribution. So actually, if there is one thing that is really unusual, it's more the first trend than the second trend. And I found that this was interesting. There's also a paper by Mark England and colleagues who is going to be or has been accepted that is making a similar point. But so just to say that we expect, even in a warming world, to have trends that are even positive for a 12-year period, and that's not something to be forgotten about. Then the next question that Patricia wanted to answer is the ability of the models to predict those internally generated fluctuations in sea ice extent trends. And so she looked at many, about 10 models from the Decadal Climate Prediction Project, DCPP. So that's a MIP of the CMIP exercise that really focuses on those models that have the capacity to initialize predictions and to run predictions taking into account the state of the system at any time. So there are several models participating to that effort. And the conclusion so far is that if you believe that fully coupled uninitialized climate models have biases, this is even worse. So these DCPP models are basically doing everything you could imagine. Here we are looking at the root mean square error skill score. So it's a score that quantifies the ability of the model to beat a climatological root mean square error, if you like. And what you expect, what you would expect normally, is that the root mean square skill score would increase over time. Sorry, would be high at initial time and would decrease back to climatology towards zero as time progresses. And here we have all possible types of behaviors. Yes, it's very funny. We have models that have very high root mean square skill score at the beginning, and that reaches zero but then overshoots to negative value, which means worse than climatology. We have this model here, the HADGEM model, that starts with a very negative root mean skill score. So it means it is worse than climatology in the first year, but then becomes better than climatology, probably due to an adjustment of the mean bias. We have models that stay negative, which is bad for all the lead times, models that say positive for all the lead times, and finally models that behave as we expect, like the North CPM model. And we looked a bit into the data, and the problem is that all these models use different methods of initialization. A few of them do full field initialization, others do anomaly initialization, and then they really tend to overshoot or to go back to their own climatology very quickly. And the bottom line of this analysis is that predicting fluctuations at the decadal time scale for sea ice is really not as obvious as doing it for temperature, for example, or ocean temperature, because we cannot just work with anomalies. The problem with sea ice is that we are constrained to live with absolute values, and that's why we also have to fix first our mean state biases. We cannot go around that. 2 minutes? Okay. Okay. I will skip that part. No, it's okay, it's okay. I had somehow 45 minutes in mind, but I will finish by talking about ongoing model development. And that's just to talk about landfast ice. So landfast ice is that ice that is anchored either to the coast or to the ground. So we are trying to develop better tools for modeling landfast ice. I'm saying that because in the new Arctic, where there will be no ice in summer, there will still be landfast ice, and landfast ice is very important for many reasons, for communities living there, for ecosystems. And landfast ice is actually complex in the sense that it interacts with the bedrock and with the topography. It's also interesting in terms of rheology. So we do that for Arctic, but also for Antarctic, and this comes maybe the final touch of this presentation. In the Antarctic, landfast ice forms close to icebergs because it doesn't anchor on the ground. It anchors on the icebergs that are themselves anchored grounded on the bedrock. And so that means that if you want to model landfast ice in Antarctica, you need to have iceberg representation. So that's why we now have this iceberg model that we have plugged in NEMO. And just to show you, and I will finish by that, the first result that we have obtained. So we have put icebergs as Lagrangian particles in the ocean sea ice model. And then we have activated the process by which icebergs can get locked by the sea ice. So when sea ice is compact enough, it could actually capture the iceberg with it, and the iceberg and sea ice would move in synchrony. And when we do that, we notice a very significant change in the trajectory of icebergs. And this is interesting because it means that also the freshwater fluxes between the no locking versus the locking simulation are going to be very different, much more equatorward freshwater fluxes due to the fact that this sea ice is transporting the iceberg, and also probably a lot of changes in the Weddell gyre here. So I think I will leave it here. And yeah, maybe as a slide of conclusion, but we can take that during the questions. Many interesting questions coming ahead, I think, for the next decade. Yeah, let's continue the discussion like that. Sorry, I didn't manage the time, but it's okay.
Awesome. Thank you, Francois. It is a 45-minute slot, but I want to keep some time for discussion.
Good.
So we might be able to squeeze you in one of the two slides if we get some good questions. Lily, go ahead.
Hi, Francois. Thank you. I learned a lot. I'm very curious about kind of the first vignette you showed around the Ross Sea.
Yes.
I think maybe this is a place where sea ice folks and oceanographers can talk more, because in the Southern Ocean, the polar front is like defined hydrographically by the like extent of winter water, like which is set by where sea ice is. And so I'm curious if in this example, if you looked at the response of the polar front's like location to to this.
No, we didn't look at that. And you mean like the ACC itself, or?
Yeah.
Okay. No, we didn't look at the location of the ACC. That said, I think we would have noticed if it would have played a strong role. But that's something we could actually. Look for the next.
Yeah, I'm thinking of being more a response than a cause.
But the response to the minimum sea ice
yeah,
extent?
as in like a sea ice minimum would result in potentially more meandering of the front or something. To that
Okay.
extent.
Yeah.
We should talk more because I think that'd be curious to investigate.
Yeah.
I have a question for your second part, extreme event stuff.
Yep.
So what do you think about the mechanism you propose could be used to explain 2007 and 2012 event in reality? Is it relevant, or is it a totally different thing?
Whether 2007 and 12 are driven by the same mechanism?
Yeah.
No, they are probably not. We're actually doing at the moment an intercomparison between the mechanisms that could explain sea ice lows. So we do the intercomparison between Arctic and Antarctic, but also Arctic for 2 different years. And we found that 2007 was largely caused by interplay between dynamics and thermodynamics, but that actually the total mass of sea ice in 2007 was higher than climatology for that year. It's just that the ice was highly compacted or converged by the currents. And so the area was indeed a record low, but the volume itself was not low at all. I mean, it was lower than in the 90s, but it was not a record low. While in 2012, it was really the mass of sea ice that decreased, mostly due to thermodynamic factors. So I think this illustrates that you could have two records for totally different reasons, and that we shouldn't just stop at the number sea ice extent by itself.
Come in. Do you have a question? Yeah.
Still too short. I want to continue on that part. You show a nice diagram, I think is the next slide, where you showed like like events going one after, anomalies going one after the other. I'm not familiar with this method. I should start with that. But how can you know what is kind of a driver versus happening at the same time because it's driven by the same thing? I mean, you have a at the end you were saying something about the Beaufort gyre, for instance. I mean, you could just imagine that you have less sea ice, you force it more directly, and then it spins up or something like that. So, how can you actually distinguish what would be a driver versus what happened because it's driven by the same thing?
Okay, so I think that the method cannot really disentangle causality. That's the first thing to notice. And also, you are constrained to seek for extremes in the state space where your model is at initialization time. So if we initialize the model in March with a given sea ice thickness and a given already, heat content in the Beaufort gyre, we know that we are going to sample extremes conditioned on that initial state. So we might miss actually even more extreme sea ice states just because we have not sampled other initial states. So that's I don't know if that answers the question, but when we find the importance of the Beaufort gyre mechanism, it is, I should put it more this way, like the sea ice extreme happen in particles that have witnessed or that have undergone a very strong dynamic influence in the Beaufort gyre. But it's not that to experience extreme sea ice state, you need to have the strong Beaufort gyre. So I would really see is it neither as a sufficient nor necessary condition. It's a player that co-occurs with the sea ice, but probably is not sufficient nor not necessary to generate the extreme.
Thank you.
All right. I'll say my name, Alex Roble. Yeah, you can stay on this because I also have a question about it. In this particular study, you are interested in sort of like one-year anomalies or rare one-year anomalies. Yeah. And I'm sort of curious about the longer timescale question about thinking about sort of the distribution. I mean, you kind of get at this later, but I'm thinking about, using this method about thinking about what constitutes a rare decadal anomaly in sea ice, right? Because and I don't know what's included in this particular model that you're using, in this method, but right, there's these longer timescales in the problem, particularly coming from the ocean and how much heat's being taken up in the Arctic Ocean. And so do you think that you could use a similar method to understand what would constitute sort of a rare, or what to characterize the distribution or the tail of the distribution of, like, let's say, decadal anomalies in sea ice? And could that help you to then start to understand some of these other questions that you are asking about, how likely is it that in a given decade we could expect to have one of these, excursions towards, let's say, no summer sea ice or something like that?
Yes, so practically and technically, it's not complicated to do that beyond the season. So we could actually continue to apply the algorithm for several years in a row. Methodologically, it's a bit more complicated in the sense that it's quite expensive in terms of CPUs. Just to give you an idea, we need 600 ensemble members to get statistic to avoid ensemble degeneracy. We have the same in particle filtering in data simulation. If you use too few particles, they will tend to just stick to each other and degenerate to one state, and so you won't be able to stimulate the ensemble enough to explore the state space. So it's very expensive, and that's also why maybe it's only possible now to do this kind of experiments, is because we need a lot of ensemble members. Then there is the scientific question. So the method works as follows. You integrate your particles and you look at what we call an observable, and in that case the observable is the CS extent, one number. And then you kill the particles based on their CS extent. So the assumption is that the observable, by minimizing the observable, you get to the most extreme observable in the end in September. But in reality, we know that there is that the CS extent in September is influenced by other factors than the CS extent itself. Sea ice volume, sea ice thickness distribution, maybe oceanic heat transport. So to do things cleanly, you should actually, for the multi-annual experiment, you should actually choose an observable that you know is highly correlated to your sea ice extent 5 or 10 years later, and make sure that by doing so that you actually push your model to the most extreme state. So I anticipate that if we want to do that, let's say for 5 years, we might encounter problems because, for example, after the first minimum in September, we will keep minimizing the CS extent, but in winter the CS extent is not a predictor for the summer CS extent next year. So we might just end up in a sort of local minimum, and we will be missing other factors that could explain the long-term and fast decline.
Yeah, I guess one comment about that is that I guess if you gave this analogy to like ensemble collapse in data assimilation, and I think if your Lyapunov exponent is negative, and so you expect everything to converge to the local minimum, as you're saying. But on the longer time scale, right, in this particular system, you might expect, and in fact want to probe whether this system is going the other way, right? If you have a positive Lyapunov exponent, and so your ensemble would actually not collapse on those time scales. So it might be worth at least doing the experiment anyways, even though I get that you're saying it's computationally expensive.
I would try it definitely, yeah.
Yeah, okay. Thanks.
And also I think,
Finish that thought, but then we'll get Earl to give the last question, and then
I was
we'll
just
wrap
about
up
to say that they have been doing similar experiments with the EMOC, where they actually applied the kill and clone algorithm and then unleashed everything. So they just turned off the algorithm to see to what extent would the particles go back to climatology, and they found with the EMOC that half of the particles go back to a normal EMOC state and half of the particles stay in a low EMOC state. So we want to do that as well for the Arctic sea ice. There's been evidence from previous work that Arctic sea ice is fully recoverable, but we would like to question that with that algorithm too.
So I had a question about some of the results in the latter part of your presentation about how sea ice changes when it's attached to grounded icebergs. Yeah. And you show this really interesting pattern in the freshwater fluxes. Yeah. Can you just explain what's going on here and the pattern in particular in the Weddell Sea? Yeah, sorry for being very fast on that. So here we are looking at a difference between two simulations. The first simulation is the simulation without sea ice locking, where the icebergs are agnostic of the presence of sea ice, so they're just making their way into the ocean. They are transported by ocean currents, but they are not interacting with sea ice, and sea ice is not interacting with icebergs. And then the red, the second simulation is the simulation where the icebergs are sometimes locked by highly concentrated sea ice. And so here we have a figure showing the difference between these two simulations. So locking, no locking minus locking. And what is shown on the map is the freshwater anomaly received by the ocean due to the fact that icebergs melt. So what we see is that the sea ice locking mechanism tends to produce more offshore melting, because ice is trapping icebergs and is bringing it with the ice pack is globally divergent, so it's bringing the icebergs equatorward, and it's creating an anomalous
amount of melting. And actually you see that if you ignore that process, along the coast, you see a lot of negative values of freshwater flux because most of the icebergs stick in that region in the no-locking experiments. They are just affected by the coastal currents, actually. And the last element I think to look at is here. So we have the Weddell Gyre, and it seems that in the no-locking simulation, we have most of the icebergs going this way. So they are just following the ocean currents, but with the ice locking mechanism, they are trapped in the Weddell Gyre, and so there is a net shift of the icebergs from here to here, again due to that mechanism.
All right, very good. Thanks so much, Francois. Let's thank Francois one more time and all of the speakers today.